Okay, so hello and welcome back. So basically there are 3 exercises left here, number 13, 14 and 15. So question number 13 is basically, question number 13 is if A is equal to, if A is a matrix alpha, beta, gamma and negative alpha, is such that A squared is equal to I, then basically you have a couple of choices. Then choice A is basically 1 plus alpha squared, and this is 1 and not I. 1 plus alpha squared plus beta gamma is equal to 0. Choice B is 1 minus alpha squared plus beta gamma is equal to 0. Choice C is 1 minus alpha squared minus beta gamma is equal to 0. And choice D is 1 plus alpha squared minus beta gamma is equal to 0. So we have basically A squared is equal to I. So of course A squared, if I have A squared is equal to I, that means that A times A, which means basically alpha, beta, gamma and negative alpha times the same times itself, alpha, beta, gamma and negative alpha is equal to I, which is equal to 1001. Now multiplying this row by this column, I get alpha squared plus beta gamma, and multiplying this row by this column, I get alpha beta minus alpha beta. This row by this column, I get alpha gamma minus alpha gamma. And this row times this column is, okay, so basically alpha gamma minus alpha gamma, and then multiplying this row by this column, you'll get beta gamma. You'll get beta gamma times plus alpha beta gamma plus alpha squared, right? And that is equal to 1001. Now what we are looking for here is, first of all, I know that based on these matrices, of course, this would be 0, this would be 0, so I know that alpha squared plus beta gamma, alpha squared plus beta gamma is equal to 1. And also we know that basically beta gamma plus alpha squared is equal to 1. Which means that 1 plus alpha squared, that cannot be right. Because if you take alpha squared to the other side, this becomes negative alpha squared, so this cannot be right. And 1 minus alpha squared, 1 minus alpha squared, that cannot be right either, because you would have to get this also as negative because of this equation. And 1 minus alpha squared minus beta gamma is equal to 0, so this is correct based on what we have here. And 1 plus alpha squared minus beta gamma is equal to 0. That is also wrong, so the correct answer is C, right? So that was question number 13. Now question number 14 is if the matrix A is both symmetric and skew symmetric. So question number 14, if the matrix A so we have, if the matrix A is both symmetric and skew symmetric, then A is a diagonal matrix. Then A is a choice A is a diagonal matrix. Choice B is a zero matrix. Choice C, A is a square matrix. Choice C, A is a square matrix. And choice D, none of these. Right? Now, this is basically, we are saying that A is symmetric and also skew symmetric, meaning that A prime is equal to A, and also A prime is equal to negative A. That means that you can write basically A prime is equal to A is equal to negative A, right? So this means that basically now the way that you can answer this question, you know that basically in the case of a zero matrix is always symmetric and skew symmetric, meaning that of course A is equal to negative A in the case of any square, any zero matrix of any basically dimensions, and also A is equal to A prime in the case of any basically zero matrix, meaning that, for example, if I have a zero matrix as 0 0 0 0 0 0, a 2 by 3 matrix, the transpose of this matrix is going to be I will take this row and make a column, and I will take this row and make a column, and therefore I will get the 3 by 2 matrix. But I suppose in the case of a zero matrix, the dimensions of the matrix is not really important. A zero matrix is a zero matrix of any dimension, and it is denoted by O, right? And if that is correct, which is the only assumption that I can make here, because here in the solutions I can see that it says that we know that only a zero matrix is always both symmetric and skew symmetric, hence the option B is correct. That's why I'm saying this. Otherwise, I haven't explicitly read anywhere that a zero matrix is I know, well, loosely, that when you write O in some matrix equation, you can replace O with any zero matrix of any order, right? Which means that it doesn't really matter whether you write a zero matrix as a 2 by 3 matrix or a 3 by 2 matrix, meaning that they are practically the same. And therefore I can say that in the case of a zero matrix, basically A is always equal to A prime, and also A is always equal to negative A, and therefore B is the correct answer here. In the case of basically other matrices, basically that's not always the case. For example, if you go for A and C, so first of all, a diagonal matrix is a let me take a look at the definition here. So basically, a diagonal matrix, as we discussed before, is a square matrix. In which all of its non-diagonal elements are 0. Any square matrix in which all of the non-diagonal elements are 0 is called a diagonal matrix. For example, negative 1, 0, 0, and 2 is a diagonal matrix, because this is the diagonal of the matrix, and all of the other elements except for the diagonal of the matrix are 0. And also, for example, you can have negative 1.1, 0, 0, and 0, 2, 0, and for example 0, 0, 3, right? And this is the diagonal of the matrix, and you can see that these elements are 0 and these elements are also 0. These are called diagonal matrices. So now what we are saying here is that A prime is equal to A is equal to negative A, and of course that's first, I mean, at least this part is not true in the case of every diagonal matrix, which means that I can rule this out, meaning that, for example, I can simply take this matrix and write it as, for example, the negative of this would be positive 1, 0, 0, and negative 2, which would not be the same matrix. So that doesn't work for diagonal matrices. And a square matrix, the same story, meaning that if I take this as a square matrix, again, A is not equal to negative A, and therefore it doesn't work for square matrices, it doesn't work for diagonal matrices. It does work for, however, for 0 matrices, and that's the end of the story. But you need to understand the fact that basically a 0 matrix, which is usually denoted by O, can be, because this is the reasoning that I'm using. I'm not really sure that if that's the valid kind of reasoning, but I know that when I write O in a matrix equation, that O can be substituted with any 0 matrix of any order. That means that, for example, if your 0 matrix is of the order 2 by 3, that's the same thing as of a 0 matrix of a 3 by 2, and therefore then you can say that, for example, in the case of any 0 matrix, that A prime is equal to A, and also negative A is always equal to A, because these are all zeros, so you don't have any problem with the sign. So that's basically that. Now, then the last question here is question number 15, and that is question number 15, and that is, if A is a square matrix, if A is a square matrix of such that A squared is equal to A, this is an interesting question actually, then I plus A whole cube minus 7A is equal to choice A is A, choice B is I minus A, choice C is I, and choice D is 3A. Now it's very interesting that now I don't really, but it seems that it works. And what I'm referring to is that when you write I plus a whole cube, that you can actually expand it as a simple basically I mean, it's just like, for example, you write a plus b whole cube, and here you have real numbers, and then you know that this normally is a cube plus, for example, b cube plus 3 times a squared b plus 3 times ab squared, right? That we already know for real numbers. Now it seems that it actually works for matrices, at least when one of these is the identity matrix, meaning that if I write, for example, let's say that I write, for example, I plus a, and let's say that a is the same is a matrix like, for example, 1, 2, 3, and 4, right? And I write it as whole cube. That, of course, is going to be equal to, I mean, if I write the matrices, well, it would be 1, 0, 0, 1 plus basically this matrix, which is 1, 2, 3, and 4. And if I raise this to the third power, that would be equal to basically 1 plus 1 is equal to 2. And here you get a 2, here you get a 3, and here you get a 5. Raised to the third power. And then if you raise this to the third power, that means that you have to multiply it by itself, meaning that you would have basically 2, 2, 3, 5 times 2, 2, 3, 5 times 2, 2, 3, 5. And that is the same thing as, now if I do, for example, the first part over here as, for example, 2, 2, 3, 5 and times 2, 2, 3, 5, what I will get is 2 times 2 is equal to 4, and 2 times 3 is equal to 6. Then this row times this column, that is 2 times 2 is equal to 4, and 2 times 4 is equal to 10. And then you have this row times this column is 3 times 2 is equal to 6, and 5 times 3 is equal to 15. And this row times this column is 3 times 2 is equal to 6, and 5 times 5 is equal to 25, which is equal to 10, 14, 6 plus 15 is equal to 21, and 6 plus 25 is equal to 31, right? Now if I take this matrix and multiply by a again, I'll get 10, 14, 21, and 31, and multiply it by 2, 2, 3, 5, and that gives me basically this row times this column is 20 plus 14 times 3 is equal to 30 plus 12 is equal to 42, and this row times this column gives me 20 plus 5 times 14. 5 times 14 is equal to 70, and this row times this column gives me 42 plus 3 times 31 is equal to 93, and this row times this column gives me 42 plus 5 times 31, which is equal to 155, right? 155. And that is the same thing as 42 plus 1 is 62. That is 70 plus 1 is equal to 90. 42 plus 93 is equal to 135. And 42 plus 55 is equal to 197. That is basically a cube, or yet better to say it's the same thing as it is basically 62, 90, 135, and 197. Now, as it turns out, you can actually use the formula that we have to expand this instead of raising it to the third power, and basically instead of adding the two matrices first and then raising the matrix to the third power, you can actually use this formula, meaning that instead of writing it this way, you can, of course that would be a lot of work, but we will do this in order to verify this. Okay, so now if I write this as basically a cube plus b cube, meaning that I write this as basically a cube would be I cube plus a cube plus we have already calculated here. No, we haven't. Okay, plus 3 times a squared b, which is equal to a squared b would be I squared times a. 3 times I squared times a plus 3 times I times a squared. Right? So of course you know that I cube is the same thing as I, of course. That is the same thing as I. And then you have a cube, and then you have 3 times, now I squared is again equal to I, and I times a is again I'm not really sure about this. We'll have to test that out, but I times a is equal to a, of course. That is meaning that, for example, if you have a matrix, for example, 1, 2, 3, 4, and if you multiply it by, for example, 1, 0, 0, 1, what you will get is basically 1 times 1 is equal to 1, and 2 times 0 is equal to 0. Then you have 0 plus 2, and you have 3 plus 0, and then you have 0 plus 4, and that gives you basically 1, 2, 3, and 4. So of course any matrix times I is going to be equal to itself, and therefore I can write this as 3 times I squared times a, and I squared would be I times a is equal to a, so that's 3 times a, and that's 3 times a squared, right? Now, the only thing that we need to calculate here is a squared, a cube, and then the rest is easy. I just want to verify if that actually, I know that it actually works, but I just want to verify it using an example. So now if a basically is equal to this, so then a squared is going to be equal to basically 1, 2, 3, and 4 times 1, 2, 3, and 4 times 1, 2, 3, and 4, which is equal to 1 times 1 is equal to 1, 2 times 3 is equal to 6, 1 times 2 is equal to 2, 2 times 4 is equal to 8, 3 times 1 is equal to 3, 4 times 3 is equal to 12, and 6 plus 16, right? So that is equal to 7, 10, 15, and 22. That is a squared. Now a cube is going to be equal to a squared times a, which is basically 7, 10, 15, and 22 times a, which is equal to 1, 2, 3, and 4, which is equal to 7 plus 40, and then that is actually 7 plus 30. And then this times this would be 14 plus 40, and then 15 plus 66, 15 plus 66, and 30 plus 88. 30 plus 88, which is the same thing as 37. 40 plus 14 is equal to 54, and 66 plus 10 is equal to 76. 76 plus 5 is equal to 81, and then 88 plus 30 is equal to 80 plus 30 is equal to 100, 110, 110, 118. 118, that's a cube. Now if I write this as, and therefore this is equal to 1001 plus a cube, which is basically this matrix, 37, 54, 81, 118, 81, 118, and 3a would be 3 times basically 1, 2, 3, 4. 3 times 1, 2, 3, and 4. And 3a squared would be 3 times basically 7, 10, 15, and 22, which is the same thing as 1001 plus 37, 54, 81. I'm getting a little bit worried by now because the numbers actually are getting way too large. So 3, 6, 9, and 12 plus 21, 30, 45, 66, and then you have, so you have 1 plus 37 is 38. 38 plus 3 is equal to 41. 41 plus 6, 41 plus 21 is equal to 62. So far, I think we have no problem. Okay. Then we have 54 plus 6 is equal to 60. 60 plus 30 is equal to 90. And here we have no problem either. 0, so 81 plus 9 is equal to 90. 90 plus 45 is 135. 135, okay. And then here we have 1 plus 118 is 118 plus 12 is equal to 110 plus 10 is equal to 120. 130. 130 plus 67 is equal to 797. 197. Right. So it actually does work. Now I don't really know. You could try that on your own. I don't really know if it, I think but based on what we see here, I don't really know if it would work in the case of a matrix of 2 matrices, for example, A plus B, for example, whole cube, meaning that the first matrix is not the identity matrix. You can try that on your own. I'm not really sure about that, and I haven't proved this, so I know nothing really about. I know that it does work in this way, and I'm saying that because it's, I mean, the solution, I mean, this has been used in the solutions. Now, this hasn't been proved anywhere. We have not proved it, so I'm using it with a whole lot of caution, and I'm only using it because it's been used in the solutions. Otherwise, I wouldn't use this as a general thing everywhere in mathematics, right? Because I don't really know what would happen if I did this for any other 2 matrices. Now, so what that means is that so by now we know that at least in this case, in the case where the first matrix is an identity matrix and the second matrix is some other matrix of the same order, you can actually use this formula in order to expand your matrices when it's, for example, raised to the third power. So what that means is that I'm going to now what I'm going to do is that now we know that basically a squared is equal to a, and I plus a whole cube minus 7a. We want to know what that is. So I can use, apparently I can use this formula in order to expand this, in which case I will get basically I cube plus a cube plus 3 times I squared a plus 3 times IA squared minus 7a, right? And then of course you know that I cube is equal to I, and a cube is equal to a squared times a, and you know that I squared is equal to I times a is equal to a, so you can write this as 3a, and you know that basically 3I times a squared is equal to a squared, so I can write this as 3a squared minus 7a, and then I can write this as a squared is equal to a plus a times a plus 3a, and a squared is equal to a, so that's 3a minus 7a, and a times a is equal to a squared, and a squared is equal to a, so we can write this as I plus a plus 3a plus 3a minus 7a, and this is 7a minus 7a, which is just 0, so that's equal to I, which means that choice C is correct. Well, sometimes you see interesting things. So that was basically the end of this chapter. In the next the next thing that I'm going to do is I'm going to work on the next chapter, which is on determinants, I think, if I'm not mistaken. So let me see. This was chapter 3. Chapter 4 is determinants. That's also a pretty large chapter, but then we will go through them one by one. So I'll see you in the next playlist, whatever you call it, on YouTube. Thank you.